Here we have a question involving a refrigeration system. In a refrigeration system, the evaporator receives heat from the low temperature reservoir and the condenser ejects heat to the high temperature reservoir, generally that is air. Let's call these points as 1, 2, 3, 4. And we know that our refrigeration system is using R134 as its refrigeration medium. The evaporator is operating at minus 15 degrees Celsius and the condenser is operating at 40 degrees Celsius. We are told that the isentropic efficiency of the compressor is 83% and the compressor output is superheated by 5 degrees Celsius and the condenser output is subcooled by 5 degrees Celsius. We are asked to calculate QLWin in kilojoules per kilogram terms. That means we have to find lowercase ql and lowercase win, and we have to find coefficient of performance, and in part B we have to calculate the same parameters but for an ideal refrigeration system. Let's try to draw the TS diagrams for these two refrigeration systems. Let's start with the ideal system because it's easier. In the ideal system, we know the compression starts at the saturation line and it is compression happens isentropically. So it's a vertical line here. And then we have a constant pressure process at 40 degrees Celsius. Then we have the expansion, which is isoenthalpic from 3 to 4. And then we have the evaporator operating at negative 14 degrees Celsius. When it comes to the actual refrigeration system, we have 5 degrees Celsius superheating, and then have the compression, and then we have the condenser. Let's call this point the actual exit from the compressor as point 2, and the hypothetical exit if the compressor was operating isentropically as 2s. Then we have the condenser output being subcooled by 5 degrees Celsius, and we have the expansion process in the throttling valve, and this is an isoenthalpic process. We can write these equations for both systems, QL, QH, and WN, and coefficient of performance for a refrigeration system is defined as QL divided by WN. Let's consider the ideal refrigeration cycle. We are going to find H1, H2, H3, and H4 values here. To find the H1 value, we know that the temperature is negative 15 degrees Celsius and the quality of H1, point 1, is 1. That means H1 is going to be Hg at T1 temperature. We can easily find that from the tables. And we know S2 is going to be equal to S1, which is Sg at T1 temperature. And P2 is going to be Pg at T equals 40 degrees Celsius because 2 to 3 is a constant pressure process. So we can find H2 using S2 and P2. And when it comes to point 3, we know quality of the point 3 is equal to 0. It's saturated liquid and temperature is 40 degrees Celsius. And we can find H3 using those two values. H3 is going to be HF at T3 temperature. Because process 3 to 4 is a isoenthalpic process, we can get H4 value because we know H3 value. Now we can calculate QL, QH, and WN using our previous equations. When it comes to the real refrigeration cycle, point 1 is superheated by 5 degrees Celsius from the evaporator temperature, so T1 is 20 degrees Celsius. P1 is the same pressure as evaporator, So that is going to be the saturation pressure at negative 15 degrees Celsius. Using those two values, using superheated tables, we can find H1. And when it comes to H2, we can use the pressure from the condenser. And we know point S2, 2S, is same enthalpy as point 1. We can find P2 and S2S values to find H2S. And we know the isentropic efficiency of the compressor is H2 minus H1 divided by H2S minus H1. So the only thing that we don't know from this equation is H2, so we can find H2. When it comes to point 3, we know the temperature is 35 degrees Celsius and the quality is 0. So we can easily find H3. H3 enthalpy is equal to H4 enthalpy. Now we can use our QL, QH and W in equations because we know enthalpies at points 1, 2 and 3.